Hello, my darlings. So today we're going to look at integration with trig substitutions. Now, just like with algebraic functions, if you can simplify before you integrate, you should do that. And one of the ways to simplify is to use your trig identities. For instance, if you have the integral of sine squared x plus cosine squared x dx, it's a lot easier to integrate 1 dx, which is just x plus c. If you use the Pythagorean identity, it will make your life much simpler. Same thing with 1 plus tan squared x. You could drive yourself crazy trying to do that integral, but if you replace it with secant squared x, then the antiderivative is just tan x plus c. Okay, so make sure you know your trig identities, okay, especially these, because not all of you are very up on those, so make sure you've got them, the double angle ones. Now, I want to look a little more in depth at when we have integrals involving sine and cosine raised to exponents. Now, there's 3 different things that can happen. The first one is when the power of the sine is an odd integer, okay? If the exponent on the sine is an odd integer, we're going to save one factor and express the remaining factors in terms of cosine. So, for instance, see how it's raised to the 2k plus 1? We're going to keep it. We're going to have sine squared x raised to the k. I'm going to keep 1 over here, and then I'm going to use the substitution y equals cosine x. Why am I keeping the sine x? Because it's part of the du. Du dx would be negative sine x. That's why we keep a sine separate. Okay, so we have an example here. The integral of sine to the 5th x plus cosine squared x. So according to our rule, we should take one of the signs away. So we're going to have sine to the 4th x times sine x times we still have a cosine squared x dx. Okay, now remember, this sine to the 4th x is really sine squared x squared, isn't it? And we want to change this in terms of cosine. Well, sine squared x is 1 minus cosine squared x, but since I had it to the 4th, I still have to square that. Then I still have, what did I have here? Sine x times cosine squared x dx. Now, we're supposed to use u is cosine x. That means that my du dx is the negation of sine x, and dx will be du over negative sine x. Okay, so here we go. Let's see what we can do. If we make this substitution, we're going to have the integral of 1 minus u squared being squared times sine x times, now that cosine squared x here is another u squared times our dx is du over negative sine x. Now my sine x and my negative sine x will divide out to a negative 1, which we can put up front. So in the next step, don't forget there's a negative there. And we have the integral. I'm going to bring my u squared up front. And why don't we expand this? Remember, this is 1 minus u squared times 1 minus u squared. So when we square that out, we expand that, we're going to have 1 minus 2u squared plus u to the 4th, and we still have our du. We're now going to distribute our u squared. So now we have the negation of u squared minus 2u to the 4th plus u to the 6th du. Now we're ready for an antiderivative. We have the negation of u cubed over 3 minus 2u to the 5th over 5 plus u to the 7 over 7 plus c. Now we have to make our final substitution back, and I'm probably going to distribute that negative as I go. This negative, I'm going to take it through. So I'm going to have negative 1/3. Remember, our u is cosine x, but we have to cube it. Then I'm going to have plus 2/5 cosine to the 5th x minus 1/7 cosine to the 7th x, and of course, don't forget your plus c. And there we go. Now the second option is when the power of cosine is an odd integer. And it's very similar to what we just did. So if cosine is being raised to an odd exponent, we take one of them that we're going to save, and then we try to turn the remaining cosines in terms of sine. And remember, then we use the u equals sine x, which means our du dx is cosine x, which is the reason we're saving a cosine x. We're saving that for our u. So we have here the integral of cosine to the 3rd x times sine to the 4th x. So cosine is cubed, and that's an odd exponent. So we're going to take one away, which is going to leave us with cosine squared x times cosine x times sine to the 4th x dx. Now, cosine squared, that's 1 minus sine squared x. And I'm going to switch and put the sine to the 4th x here times my cosine x. Multiplication is commutative, so I can just slide that over if I'd like. And now we let u be our sine x, which means du dx is cosine x, and dx is du over cosine x. So if we make our substitutions now, we have the integral of 1 minus u squared times u to the 4th times cosine x times our dx is du over cosine x. And what happens to those cosine x's? They're all gone. So now we're going to distribute that u to the 4th, and we're going to have u to the 4th minus u to the 6th du. Much easier to take the antiderivative when it looks like this. So now we add 1 to the exponent, divide by the new exponent, minus u to the 6 becomes u to the 7 divided by 7. Don't forget that plus c. And now we're going to substitute. Our u's are sine x, so we have 1/5 times sine to the 5th of x minus 1/7 times the sine to the 7th of x plus c. And there we go. Now the last case is when both the exponents are even. In the case where both of the exponents are even, you want to use one of the double angle identities, okay? Because it's easier to take the antiderivative of a sine or cosine of 2x than it is to take the antiderivative of sine squared x or cosine squared x. So when we have the integral of sine squared x, we're going to change that to the integral of 1/2 times 1 minus cosine 2x dx. So that 1/2 can come out front. Now some people like to split that up into two integrals so that they have a 1/2 times the integral of 1 dx minus a 1/2 times the integral of cosine 2x dx. It's up to you whether you want to do that. Now, I know we can take the antiderivative of this first one very easily. And the second one, it depends on, if you remember, the way we were doing antiderivatives before u substitutions. But since we're doing u substitutions in this unit, let's say we let the u be 2x, then our du dx is 2, and dx is du over 2. So that this cosine 2x becomes cosine of u times du over 2. So now we have 1/2 times the integral of 1 dx minus 1/4 times the integral of cosine u du. So we have 1/2, the antiderivative of 1 dx is x, minus 1/4. The antiderivative of cosine u is sine u. Don't forget your plus c. And then we have 1/2 x. Now don't forget that sine u is really the sine of 2x plus c. And now we've got it. Next up, we're looking at very similar to what we were doing before, only this time it's when we have tangent raised to an exponent times secant raised to an exponent. Notice there's also a Pythagorean identity that connects tan squared and secant squared, which we're going to use in order to do this. So if the power of tangent is odd, we're going to save a factor of secant x tan x, not just one tan x. We need a secant tan, okay? And we're going to take now the even part of the tangent. We're going to turn that into some form with a secant squared, and then we let the u be secant x. Why did we have to save secant x tan x? Because the derivative of secant x is secant x tan x. Okay, so when we have the integral of tan cubed x times secant cubed x, we have tangent with an odd exponent. So we're going to rewrite this as the tangent squared of x times, I'm going to keep a tan x. Now I'm also going to take a secant x out of the cubing one, so that's a secant squared x dx, because I'm going to need all of that for my derivative. Okay, now we should probably change tan squared to something in terms of secant. So that's the integral. Tan squared x is secant squared x minus 1. And I'm just going to switch the order here so that my secant squared x is over here. And then I have my secant x tan x next to my dx. Okay, hopefully that's okay with you. Now we're going to let our u be secant x, which means du dx is secant x tan x. So dx is du over secant x tan x. So now when we make that substitution, we have the integral of u squared minus 1 times u squared times secant x tan x times du over secant x tan x. And those secant x tan x's divide out. I'm also going to take this u squared and multiply it into that parentheses. So I have u to the 4th minus u squared, and the only thing left is our du. So our antiderivatives, now we add 1 to the exponent and divide by the new exponent. We're going to have u to the 5th over 5 minus u cubed over 3. Don't forget your plus a constant. Now we're going to go back to secants. So it's 1/5 secant to the 5th of x minus 1/3 secant cubed x plus our constant c. There we go. Now the next one here is when the power of secant is an even integer. If secant is an even integer, we're going to save a factor of secant squared x. That's because we're going to let u be tan x, which means that our du dx is secant squared x, which is why we want an even exponent on the secant so that we have a secant squared for our du dx, and we have a secant squared so we can use our Pythagorean identity. Ready? We have the integral of tan to the 6th x times secant to the 4th x. So we're going to use that secant to the 4th. We're going to keep our tan to the 6th x. We're going to split up secant to the 4th to secant squared x times secant squared x dx. The next thing we're going to do, we keep the tan to the 6th x, but we're going to change this secant squared x. We're going to use the Pythagorean identity and change that to 1 plus tan squared x. We still have times secant squared x dx. Now we're ready to use our u substitution. U is tan x, du dx, the derivative tangent is secant squared x, and then our dx would be du over secant squared x. So what do we have now? We've got the integral tan to the 6th x is u to the 6th times 1 plus tan squared x is u squared times secant squared x, but dx becomes du over secant squared x. Those secant squared x's will divide out. When I bring my integral over, I'm also going to distribute that u to the sixth, so that I have u to the sixth plus u to the eighth du. Now to take the antiderivative, we add 1 to the exponent, divide by the new exponent. The antiderivative of u to the eighth would be u to the 9 over 9. Do not forget that plus c. Then we go back to tangents. So 1/7 the tangent to the 7th of x plus 1/9 times the tangent to the 9th of x plus the constant. And there you go. I'm going to show you a totally different method that's not necessarily using the trig identities, but is using SOHCAHTOA instead. Here's an integral of the square root of 9 minus x squared over x squared. Hopefully, you can recognize that if I put an x here, then this piece has to be 3. And this side then would be the square root of 9 minus x squared, because by the Pythagorean theorem, x squared plus this radical has to equal the hypotenuse squared. Now, how did I know to put the 3 there? Because if I have subtraction, this first piece has to be my hypotenuse. If there was addition, that would be the leg squared plus the leg squared. Now, I'm going to put theta always opposite my x. I always use theta opposite my x. Now, because of that, sine theta, which is opposite over hypotenuse, would be x over 3, which means that x equals 3 sine theta. We're going to use this in just a moment. That also means that if I was to take the derivative of x equals 3 sine theta with respect to the new variable theta, that dx d theta equals 3 cosine theta, and dx is 3 cosine theta d theta. So far, are you with me? Okay. Now, so I'm able to, right now, I can replace the x squared with the 3 sine theta and square that. I can replace the dx with this 3 cosine theta d theta, but I need that numerator. So what can we use for the numerator? Well, if we look at our picture again, the numerator is that square root of 9 minus x squared. It's adjacent to theta. So if I use the fact that cosine theta is the adjacent side over the hypotenuse, then I know that the square root of 9 minus x squared equals 3 cosine theta. So now we're going to make that substitution. So we have this integral. Now this top piece, we just said that that is 3 cosine theta over this x squared, we said is 3 sine theta, but we have to square it. Dx we have over here, which is 3 cosine theta d theta. Now, let's do a little bit of multiplication here. So we've got the integral of 9 cosine squared theta, and in the bottom, if we square that, we're going to have 9 sine squared theta, and let's not forget our d theta. Okay, those 9's will divide out, and we have cosine squared theta over sine squared theta d theta. Now, if it was sine over cosine, that would be tangent, but since we have the reciprocal of that, that must be the cotangent of theta being squared. Now, I don't know the antiderivative of cotangent squared theta off the top of my head. However, I do know, with a Pythagorean identity, that cotangent squared theta is cosecant squared theta minus 1 d theta. And those I do know the antiderivative of. The antiderivative of cosecant squared theta is negative cotangent theta minus the antiderivative of 1 is theta plus c. Now, we have to go back to x's. So here's the catch. Cotangent, now you know tangent is opposite over adjacent, which means cotangent is going to be the reciprocal, the adjacent side, which is the square root of 9 minus x squared, over the opposite side, which is x. So we have the negation of the square root of 9 minus x squared all over x. Now we have to find theta. Uh-oh. How are we going to find theta? Well, remember when we said way back at the beginning, probably the simplest thing we wrote was that the sine of theta equals x over 3, right? If we want to solve for theta, we would use the inverse function. So theta would be sine inverse of x over 3. We can place that back in here for theta. Sine inverse of x over 3. And of course, we can't forget the plus c. Now that is a totally different looking answer. But it was actually easier to do the calculus in terms of trig than it would have been to do it in terms of all those x's. All right, guys, we're going to stop here. Have a great day.